Today we're going to be finding the equilibrium constant K when some equilibrium concentrations or partial pressures are missing. Yesterday we had all the final equilibrium concentrations. To do this, we're going to use ICE tables or RICE tables, which are very similar to the BCA tables that you used for limiting reactants. R stands for reactants or reaction, I, initial conditions, C, change, E for equilibrium. You either need to use partial pressures or you need to use molarities. So a flask was charged with 10 atmospheres of H2S at 300 K. All that means is that it was filled to 10 atmospheres of H2S, as shown in the table there. Once equilibrium was reached, the partial pressure of the S2 was 0.020 atmospheres. What was the final pressure of the gases? Well, we know when the reaction first starts off, at the very beginning, we have zero present of any of the products. We know that we had to have made 0.020 atmospheres of the S2. Notice that we have a 2 in front of the H2, which means that we made 2 times 0.020 of the hydrogen gas. We also have a 2 in front of the H2S, so we lost 2 times 0.020. Now notice that we can fill in the equilibrium values. So we have 9.96 and 0.040. Let's write the equilibrium expression. We're going to write that to the side. Kp is equal to partial pressure of hydrogen squared times the partial pressure of S2. Remember, we do products over reactants. Everything is in the gas phase, so we don't omit anything. And in the denominator, we have pH2S squared. Now it's simply a matter of putting in the values. So Kp is going to be equal to 0.040 squared times 0.020 divided by 9.96, and this also needs to be squared. When we do the calculation and have only 2 sig figs, we're going to have 3.2 times 10 to the negative 7th. Remember that the values for K are unitless. We have a very small value of K, so only a small portion or a small fraction of reactants are converted to products. Let's review what we did. We took the concentrations or pressures that we knew, which are shown in black, and put them into the table, and then used stoichiometry to determine the change. After that, we were able to calculate the equilibrium pressures, and from there, we could calculate Kp. In our next problem, we have phosphorus pentachloride in equilibrium with phosphorus trichloride and chlorine gas. At constant temperature, a 1 liter flask initially contained 0.298 moles of PCl3 and 8.70 times 10 to the negative 3rd moles of PCl5. After the system reached equilibrium, 80% of the PCl5 had decomposed. Calculate the equilibrium concentration of all species and the value of K. So frequently on these problems, they will give you the size of the flask. If you have moles, then you need to convert that to molarity. So always keep an eye on the flask volume because you may need to convert your moles to molarity. In this case, we did not need to. So let me write here, may need to convert moles to molarity. But we didn't need to, we were in good shape. Okay, let's see what they told us. We had 0.298 moles of the PCl3. Make sure you put things in the right column. And we had 8.70 times 10 to the negative third. And we didn't have any of the chlorine gas yet, not initially. Now they tell us 80% of the PCl5 decomposed. So what we're going to do is we're going to take 80%, which would be 0.80, and we're going to multiply it by 8.70 times 10 to the negative third. That will give us how much of the PCl5 we lost. And that value is negative 0.00696. So I can fill this in, 0.00696. I put things in standard notation rather than scientific. This is a 1-to-1 ratio, so this means that I had to have made 0.00696. And I also had to have made the same amount of the chlorine gas because everything's in a 1-to-1 stoichiometric ratio. Now I'm ready to do my math. So 8.70 times 10 to the negative third minus the change is 0.00174. The final amount of the phosphorus trichloride is 0.305. And then we have 0.00696 molar of the chlorine. We're ready to plug in to Kc, so let's write our expression for Kc. Kc is going to be the PCl3 times the concentration of the chlorine over the concentration of the PCl5. And we plug in our values. So we have 0.305 times 0.00696, and then we divide through by 0.00174. When we do that, we get a value for K of 1.22. Now, remember that if K is very large, that means the product is favored. If K is very small, it means the reactants are favored. And by very small, I mean 1 over some large number. If it's close to 1, then that means that products and reactants, there's substantial quantities of both present. So appreciable quantities or appreciable amounts of products and reactants are present. So again, to summarize what we did, we wrote down what we knew. First, we checked to make sure that we didn't need to convert our moles to molarities, and we filled in the values we knew. The 80% told us that we needed to multiply the quantity of the PCl5 by 0.80, and then we were able to use stoichiometry to fill in the other parts of the table. Our last one is tricky. So we've got this reaction here where oxygen difluoride is in equilibrium with oxygen and fluorine gas. We're told a 2-liter flask is charged with 1.2 atmospheres of OF2. So the first thing I do is go, oh, you know, is that 2-liter flask going to make a difference? Nah, because it's pressure, so it doesn't really matter. And I'm told the final pressure in the flask is 1.4 atmospheres. So the question is, what is the equilibrium constant? So here's the hint. Fill in the table with what we know, and then set the sum of the equilibrium partial pressures. That's going to be these values down here. We're going to set the sum of them equal to 1.4. So we're going to end up doing some algebra. So let's do this. Initially, we are putting in 1.2 atmospheres, and we have no oxygen, no fluorine, because the reaction has not started. We don't know exact quantities, so we're going to say X. All right. So we're going to make plus X of the oxygen, which means that we have to make plus 2X of the fluorine and lose minus 2X of the OF2. Now we can write in values. So we have 1.2 minus 2X, X, and 2X. We know that these values have to add up to 1.4 atmosphere. So we're going to do a little bit of algebra. We have 1.2 minus 2X plus X plus 2X is equal to 1.4. So 1.2 plus X equals 1.4. So X has to be equal to 0.2. All right. Now I'm going to take that 0.2 and put it into all the equilibrium values. So that means that the partial pressure of OF2 is equal to 1.2 minus 2X, which is going to be 0.8 atmospheres. The pressure of O2 is going to be 0.2 atmospheres because it's X. And the pressure of PF2 is going to be equal to 0.4 atmospheres because it's 2X. And just to make sure that makes sense, 0.8 plus 0.2 plus 0.4 does add up to 1.4. Now I can figure out my value for Kp. So let's first write the expression here. Kp is equal to, oh, I've got to write that as the correct thing here. Let me see if I can erase it. All right, go back here. All right, hopefully we did this. I have to write P, remember that? So I have to write PO2 times PF2, it is squared, over POF2, which is also squared. And I'm going back to the coefficients. So here we go. Kp is equal to 0.2 times 0.4 squared, all of that divided by 0.8 squared, and then that is equal to 0.050. So this is not an uncommon type of problem on the AP exam where you're given a total of partial pressures and then you're expected to use stoichiometry to back into the final answer.